All right, 5.4 angle bisectors. Angle bisector theorem. If a point is on the angle bisector, then it is equidistant from the sides. So that just means equal distance or the same. So things to notice is you've got the angle markers here, and you have the right angle markers, which is why it's perpendicular. The converse of that is if a point is equidistant from the sides of an angle, then it is on the bisector. Excuse me. So, and then notice what we have here is we have a right angle marker, and then we have these equidistant, the congruence markers. So you need at least two of those things to prove. You either need the angle markers, the right angles, or the congruence markers. Now, if we look at this first one, okay, we can see that can you conclude that BD bisects ABC? Now, in this case, we only have the right angle markers. We don't necessarily know what the angle is. So, again, I could have a line that goes something like this. It could intersect at a right angle, but because there is no congruence markers, there's no angle measures, okay, I really can't say much about this one, okay? So this would be a counterexample of, hey, I've got right angles, but they're not, I don't know if they meet at the same place or not. I'm not sure, so this one would be a no. Now, I agree, it looks like it, okay? It sure looks like it, but we can't say for certain. Mathematically, we can't prove it because all we have is this. We don't have anything else. Now, here we can see that we have the same number, okay? So they are the same distance apart, which means if I know that they're the same distance apart, then I have to have the same angle measures. So this one is going to be a yes because I know that they're the same distance apart, which means they have to have the same angles. And for the third example, again, in this case, I have the congruence marker and the right angle. Therefore, yes, I know that it's going to work. So if it's possible, find x, okay? Again, I see I've got enough information here to solve it. So that means that this angle is going to be the same as this angle. So I'm going to set them equal to each other and solve. Subtract 4x, subtract 4x. X minus 2 equals 5, add 2, x equals 7. And over here, again, I see I've got right angles and equal angles down here. So I know that those distances are going to be the same. So once again, I can set them equal to each other. Get x by itself, subtract 1, and I'm left with 10 equals 2x, which means x equals 5. Concurrency of an angle bisector. So the angle bisectors of a triangle intersect at a point that is equidistant from all sides of the triangle. So we kind of touched on this before, but again, if I were to draw a circle, this would be a circle that would be the same distance from all the sides. Again, that's done by finding angle bisectors. So PD is the same distance as PE, which is the same distance as PF. Note, the angle bisectors are not congruent, okay? So these red lines right here are not the congruent lines, and it kind of looks like that, okay? You can see those aren't all the same distance. However, the blue lines are the same. And so this point that we found right here is called the incenter. So point D is the incenter of X, Y, and Z. Find dB. Well, I see that DC is 9, and if DC is 9, dB is also going to be 9. They're trying to trick me with this, okay? They're trying to trick me with this. That's the angle bisector, not the distance that is equidistant from the sides. So looking at this last problem, N is the incenter. And again, what does the incenter tells me? That tells me that the center is equidistant from each of the sides. So the incenter is same distance to each side. So if I look at the diagram, that's the blue lines, So I know that this side right here, my hypotenuse, if I were to draw it, okay, I can pull it out. Always, always, always recommend doing that. This part right here is 20. That's my hypotenuse. Because I have a right angle below, I know that this is also a right angle, and this side is 16. So when we get two sides of a triangle like this, a right triangle, we can basically always find the third part using kind of a special formula, Pythagorean theorem. And it's kind of like, works like this. The classic way to think about it is a squared plus b squared equals c squared. But I also like to write it as one of the legs of my triangle and the other leg of my triangle is going to equal the hypotenuse squared. So again, whether you think about A and B have to be your two smaller sides, and then C has to be your hypotenuse. And again, the hypotenuse is always across from 90 degrees. So we know that in this case, one of the hypotenuse is 20, and one of the legs is 16. And I don't know, I'm trying to find this other one. So I'm just going to call it X. I'm not sure what it is. Well, now we're going to start simplifying, and we're going to get 16 squared to be 256. I'm going to keep this here first, or still. And then 20 squared is 400. So now I can just work on simplifying and getting x squared equals 144, which when I take my square root, I get x equals 12 or negative 12, but 12 is the correct answer in this case. We can't have a negative distance. So ND, so we found, in this case, we found NF to equal 12, but NF, NE, and ND are all going to be the same distance. So ND equals 12.